We would like to calculate the electric field due to a symmetric distribution. The distribution we're going to look at is an infinite thin plane with a uniform charge density sigma. So we have an infinite thin sheet. And we want to find the electric field on both sides of the sheet. Now, the first argument is by symmetry, that if we picked a little piece up here, dq, and if we picked another piece down here, call this dq1 and dq2, and we looked at a point P over here, this piece is producing an E field dE1, and this piece is producing an E field dE2. And so when we add these together, these two pairs of charges produce a field that points away from the sheet. Now, we can take the entire planar sheet and divide it up in pairs and have a similar calculation, which tells us that on either side of the sheet, we expect the electric field to point away from this positive sheet. And this is because the sheet is infinite. We also expect that if we took some line that's parallel to the sheet, that the electric field magnitude along these lines would be uniform. And that will help us decide how to choose our Gaussian surface. So this is what we expect from the symmetry of an infinite sheet. Now, in this problem, we have two regions, on the left and on the right. And let's put our sheet at x equals 0, and we'll call this our x-axis, and we have a unit vector I hat. And this is the beginning of the setup for this problem. And now we can apply Gauss's law by choosing a Gaussian surface. So let's draw our sheet again, plus sigma. And by the symmetry of the problem, the best Gaussian surface that we can choose is a cylinder, a little Gaussian cylinder. And we want both of these sides to be the same distance. And that way, the electric field on both sides will be the same in magnitude by the symmetry. Remember that the unit normal on this end cap points out, and the unit normal on that end cap also points out. And our Gaussian surface has three different faces, two end caps and a body in which the unit normal points out on the body. But because the electric field is tangent to that, there'll be no flux through the body of the surface. And so now we can apply Gauss's law, where we're calculating the flux dA. This is through our GS. We'll call GS the Gaussian surface. Makes it a little bit easier. And over here, we have the charge enclosed in the Gaussian surface divided by epsilon naught. Now, it's always a good idea to illustrate where that charge enclosed is. It's where the sheet intersects the Gaussian surface. And now flux, E is pointing outward. E is pointing outward. It's the same magnitudes. If we make this area of the cylinder A, then we have EA on the left plus EA on the right, and through the body, 0. Now, the charge enclosed is just our sigma times the same cross-sectional area, and we're dividing by epsilon naught. And Gauss's law equates these two different physical quantities. And so we get 2EA equals sigma epsilon naught A. And so what we have in Gauss's law is the magnitude of the electric field. Now, because this quantity was positive, it agreed with the way we chose our arrows. But notice that the direction of the E field is in opposite directions. And in our regions 1 and 2, this side x was negative, this side x was positive. We now want to express the fact that an electric field think of it as an arrow in space at every point in space. And we need different descriptions for the arrows on the left side compared to the right side. And here's how we would write our answer now. We would say that the electric field for x positive is sigma over 2 epsilon naught I hat. That corresponds to pointing in the plus x direction. And on this side, same magnitude, but minus 2 epsilon naught I hat for x less than 0. And that's how we can express the vector fields for all of space. But notice that there's this discontinuity at x equals 0 because this is a very thin sheet. And in fact, if we made a graph of the x component of the electric field as a function of x, we see that that component is negative. There's a discontinuity here, and on this side, it's positive, and the value here is sigma over 2 epsilon naught, and the value down here is minus sigma over 2 epsilon naught. And so that's the electric field for a single thin sheet using Gauss's law.